Okay, so the plan for today is just to finish up chapter 6, finish up solving simple interest applications and 6.5 solving proportions and their applications. The Unit 2 exam scores are updated. I went through them yesterday and added partial credit. So if you haven't seen already, you can check back on WebAssign and check your updated exam score. And the quote of the day today is one quote and one related idea by philosopher David Hume. The quote is, "A wise man or a wise person always apportions their belief to the evidence." Um, and I think particularly, we're one of the reasons that we study math, as we see in these next couple of sections, is the application to the real world, right? We construct models that help us to maybe understand the real world and make inferences or predictions a little better, a little more accurately. Um, And we should be careful that the models and that whether it's a formal model in the form of, like, say, a simple interest calculation, or a more abstract model in the sense that we just have a certain worldview, a certain way that we think about the world, we ought to take a little bit of effort to make sure that that's in line with the actual evidence that's in the real world, at least for important things that we want to get right. Um, so I think that's the idea up here. In probability and statistics, we talk a lot more about this. So in Math 165, we talk a lot about evidence in favor of something or evidence against something, or investigate what that really means in some different contexts. Also, I think that, when we're talking about modeling or understanding the real world, there are a couple different facets to that. There's this idea of Hume's guillotine, sometimes called the is-ought problem, that things like science and empirical study are good at answering is questions or making is statements. This is true about the world. Gravity works this way or nuclear physics works that way. But just because we know the answer to an is statement, or even maybe a very difficult is statement, we got the answer to that through, say, science, that doesn't tell us what we ought to do with that, right? We understand nuclear physics. Should we make a nuclear bomb or should we make a nuclear power plant? What ought we do with that knowledge, with that information? Uh, so that's that ought idea, takes the kind of raw materials of what science gives us to work with and says, how should we put those materials together to create a society, a world, in which we'd like to live? And I think that's, much the part of, say, general education and, the study of, philosophy and literature and so on, to try to round out, this idea of what ought we do with what we discover from our, physics and chemistry and biology, and maybe even, using mathematics as part of that. Okay, so moving on to section 6.4, solving simple interest applications. So recall that our simple interest formula is I equals PRT. Interest equals principal, the amount of money that we invested or that we owe, times rate times time. Okay, so let's look at kind of, I guess, a warm-up problem a little bit. In 25 years, a bond that paid 4.75% interest per year earned $2,375 in interest. What was the principal of the bond? So how much did we originally invest in the bond to earn this much interest over this time at this rate? We note that we're given the time frame in years and the interest is per year, so everything meshes. So if I have I equals P times R times T, the amount of interest I got was $23.75. That equals the principal. That's what I don't know, what I'm looking for, times the rate times time. So times 4.75% times time of 25. So we have number times variable equals number. We divide by the coefficient of the variable. We divide by 4.75 times percent times 25. And I need to simplify this. It looks like 2375 has a factor of 25 in it. So let's try to do that ratio first. So I'm going to try to write 2375 as 25 times something. And that should give me a much more manageable number to work with to divide out my 4.75%. Okay, does 25 go into 2? No, it doesn't. Into 23? No, it doesn't. Into 237? Yes, it does. So 25 goes into 237. Well, 25 times 8 is 200. One more would give me 225. I think that is 9 times. 10 times 25 would give me 250. And if I had a 250 here, I would have had a 25 there, and I would have gotten one the next one over. So I just missed that. So I'm right up here at 9 times that 25 goes into 237. 9 times 25 is 225. And this gives me 12 left over. Bring my 5 down. 25 goes into 125 5 times. And I get 25 times 95. So 2,375 is 25 times 95. And I can divide out my common factor of 25 from the numerator denominator using my equivalent fractions property. So I see that now my principal is 95 divided by 4.75%, or that's 0.04, let's say 475. And now I want to divide by a decimal. I need to move my decimal point over. So I move it to the right 4 places. And I have 95, 0.0000. So I have 950,000 divided by 475. Okay, let's work on this. We could do long division right away. We could also start working on this with by dividing out some common factors. I think it's probably a coin toss which way you'd rather do it. I think I'll try to split off maybe a factor of 5 and then another factor of 5, see where that gets us. So 475, that's almost 500. So it's almost 5 times 100. But 475 is 500 minus 25. So that's 5 times 100 minus 5 times 5. Or that should be 5 times 95. And hey, actually, I realized that by splitting that 5 off, I was planning to divide a 5 out of 950,000. But I actually said the 95 is going to work a lot better. 950,000 is 95 times, 10,000. So my 95s will actually divide out. And now 10,000 divided by 5, well, that's just 2,000. So our original investment was $2,000, and we earned even more than our original investment in interest. Does that make sense? We usually think of the amount of interest we earn as a small amount, not more than the original amount we invested. But remember, we invested this for quite a long time, 25 years. So if we were paying, say, 4.75% is about 5% interest per year over 20 years, so 1/20th per year times 20 years, that would be the whole amount that we have invested that we would get back as interest. Yeah, this does seem about right. We earned more interest than we had invested, and that was mainly because of the really long time that we left it invested. So time is one of the factors you can control with investments, but you can only control it kind of on the front end, right? If you want to have a certain amount of money by age 60, you can control it on the front end by saying, well, when I'm a bit younger, I'll put a little more money away, be a little more frugal, and that'll pay big dividends later on, when I'm ready for retirement. Uh, and as an aside, if we were to look at compound interest instead of simple interest, which is usually the kind of interest that we would get on an investment over a long period of time, the effect would be even greater. The effect would be even more magnified from investing earlier, from having a longer time horizon. So we typically would prefer longer time over even longer principal or even kind of higher interest rate. Obviously, all of those contribute to having more money in the account, but time is even more important of a factor when we get into compound interest. Okay, so next example, this one's a little more complex. Diego invested $6,100 in a 9-month certificate of deposit, paying 1.8% interest per year. How much interest did he earn from this investment? From this investment. Well, here we have a little bit of a mismatch in our times. We have a 9-month certificate of deposit paying an interest rate per year. So what is my time going to be? 9 months. My interest rate is in years. So let me put this in years. 9 months is 9/12ths of a year. How did I do that? Well, I mean, one way is just to kind of realize that 9 months is 9/12ths of a year. I can multiply 9 months by 1. If I multiply by 1, I don't change a fraction. I can multiply it by, say, 12 months over 12 months. I think we all agree that that's 1. Same units, same number. It's the same thing over itself. That's just 1. But then I could say, well, 12 months, I have another word for that. I have another unit for that. I could really just say that's 1 year. So in the numerator, I choose to represent the idea of 12 months as 1 year. And the denominator, I choose to represent the idea as 12 months. And I see my units of months divide out. So I have 9 over 12 years. So by writing the number 1 in a creative way, I can change my units around if I need to. Or I could just think through 9 months is what proportion of a year, that's 9/12ths of a year. So we want to know how much interest did he earn. So I equals principal 6,100 times rate 1.8% times time, which we're going to write as 9/12ths. This way we have 1.8% per year times 9/12ths years. The years unit divides out. And I have 6,100. I'm going to choose to represent 1.8% as 1.8 over 100 times 9/12ths. And the 6,100 divided by 100 would give me 61 times 1.8 times 9/12ths. I think I'm going to go with thinking of 1.8 as 18 divided by 10. And I see that, 18 divided by 12, well, I guess I could do 9/12 as 3/4. That might help. 61 times 18 times 3 over 10 times 4. The 18 has a factor of 2 in it. 18 is 2 times 9, 4 is 2 times 2. And in the numerator, we get 61 times 27 over 20 in the denominator. Okay, so let's multiply 61 times 27. 7 times 1 is 7. 7 sixes are 42. 2 times 1 is 2. 2 times 6 is 12. So I got 1,647. And I suppose I could think of 20 as 2 times 10, just like over here. Or this is 1,647 over 2 times 1/10. That 1/10 will be easy to work with at the end. I'll just kind of leave that off to the side. And I know that 1,600 divided by 2 is 800. 40 divided by 2 is 20. And 7 divided by 2 is $3.50 or 3.5. And that's divided by, I guess I don't need parentheses if I'm doing divided by 10 like this. That 10 just says bump my decimal place 1 to the left. So Diego would have made $82.35 from this 9-month investment in a certificate of deposit at $6,100 principal. So a certificate of deposit is just kind of like a savings account in a bank, but your money is locked down. So where you put your money in a savings account, you can go into the bank and take it out pretty much anytime you want. Certificate of deposit, you're just locking that money down for, in this case, 9 months. So often it's something that retirees will do because they want to have an amount of money that's pretty close to being like cash that's not invested in the market that might go up and down a bunch. But also that they want a little better interest rate on than, just what a checking or savings account would pay, which is usually pretty close to zero. So 1.8% might not sound like a lot, but you see that even over just 3/4 of a year, $82 is, hey, that's a phone bill or something like that was covered just by interest. If you were sitting that money in a checking account or something like that, then you wouldn't get any interest on it. So there are strategies like rolling CDs where, if you buy 1-year CDs, but you buy them every 2 months, then kind of every 2 months you have like 1/6 of your money kind of free up, and you can either choose to keep it in cash in a savings account if you need access to that money, either kind of right now or in the upcoming month or two, or you can put it back into a 1-year CD and kind of keep it rolling along. So there are different investment strategies like this that folks use, and CDs, like I said, are usually geared towards retirees. Most people would say that if you're younger, if you have a little higher risk tolerance, maybe investing in the stock market is going to do a lot better for you over even an intermediate term like 5 or 10 years, but certainly over a long term. CDs feel a lot safer though, because you kind of know up front what the bank is saying they're going to pay you. Okay, so next example, AIRIN, AIRIN. I just take these problems right from the book. So that's the name that the book came up with, AIRIN. I'm not sure if I'm saying that right, but borrowed $3,900 from her parents for the down payment on a car and promised to pay them back in 15 months at 4% per year rate of interest, we're always assuming simple interest here. How much interest did she owe her parents at the end of this loan? So again, I equals principal times rate times time. We're looking for the amount of interest she owed. So I equals, the principal is $3,900. The rate is 4% per year. And the time, 15 months. We can do the same kind of thing. We want to get rid of the months. So I want months on the bottom. And I want to end up with years as my unit. So I want years on the top. 1 year is equivalent to 12 months. So if I put the same thing in the numerator and denominator, but just phrased different ways, 1 year is equivalent to 12 months. That is just a multiplication by the same thing over itself, or 1. That doesn't change the amount of time. I get 15/12 of a year. I can divide a factor of 3 out of the top. 5/4 of a year. 5/4. Or I see interest is 3,900 times 4/100. I'll choose to think of 4% as a fraction here, because that will mesh well with the 3,900, which is 39 times 100, times 5/4. My 4's divide out. My 3,900 divided by 100 just gives me a factor of 39. So the interest that she'll owe, the 4's divided out, the factors of 100 divided out, she'll just owe 39 times 5. One thing that we can do to make things a little easier is if I multiply numerator and denominator by 2, 39 times 5 times 2 over 2, I see 5 times 2 gives me a 10. Or that's 390 over 2. That's like 400 minus 10 over 2. 400 over 2 is 200. Minus 10 halves is minus 5. So that should be 195. And that's in dollars. So this $3,900 loan for 15 months at 4% interest per year, simple interest, she'll owe an additional $195 to her parents at the end of the term. Any questions on any of these problems? So the text actually had a couple of good writing exercises, so I copied them over here. And a couple of good questions, right? Why do banks pay interest on money deposited in savings accounts, and why do banks charge interest for lending money? Kind of an interesting question. And how do they pay interest on money deposited? How can they afford to pay you money? Pay you interest on your deposits? Well, the first question, why do they pay interest on money deposited? Well, the short answer to that is to get you to deposit more money. They want to, if you could choose to invest your money in maybe a money market account or something like that with an investment firm, or you could choose to put your money in the bank, they would rather have you put your money in the bank than put it somewhere else. The more money the banks have on deposit, the more loans they can make. And banks make money by originating loans, and all of the points and things, the fees and so on the front end of the loan is where they make a lot of their money. So the more mortgages and personal loans and car loans that they can write, the more money they make, and they can write more of those loans if they have more deposits. So basically, when you see that, you have $1,000 in your account at the bank, they don't have $1,000 sitting in some little drawer in the safe with your name on it. They've taken most of that $1,000 and lent it out to somebody else. That's also one of the issues with like the savings and loan crisis, or you've seen a couple European countries recently. I think Greece was one recently, maybe France or Spain, where they were worried about a run on the banks, as they call it. So if everybody who has deposits in a bank shows up at the door that morning and says, I want my money out right now in cash, hand it to me, the bank can't do that because they've taken, maybe the deposits that they have and they've lent back out 90% of that money. So they keep a reserve rate, they keep a reserve amount so that if people come in and say, I want money out of my account, they can give them money. They, have to be able to do that reasonably, but they don't keep all of that money in cash. So why do they charge interest for lending money? Well, because they need to make a spread. So if they're going to pay you money for your deposit, you're depositing $1,000 into your account, and they're saying, okay, we'll pay you 1% interest per year on this account, the money you have in this account. Well, when they turn around and they lend out, say, $900 of that to somebody for part of a mortgage loan, well, they have to charge that person interest so that they have the money to pay you, so that they have the money also to pay their employees to keep the lights on and all of that. So that's the way that, roughly speaking, banks make money. These days, it's a little more complicated than that. Banks, often don't actually make the money from the interest. Often banks will wrap the mortgages together and then they'll basically sell those mortgages off to investors, on Wall Street. So you can buy a part of a pool of, 10,000 mortgages all bundled together. And this practice, and particularly the analysis of the risk in such a practice, was one of the things that contributed to the housing market crisis in 2007, 2008. Just underestimating the amount of risk in these debt obligations. So, that's a little bit of the background on kind of how banking works. Banks create money in a sense by taking your deposits, lending them out to somebody else. That person, goes and, buys the house off of somebody with that cash they lent out. That person that they paid then takes that cash, puts it into the bank, and the bank takes part of that money and lends it out again. And so banks can create money in this way. So there's a lot of interesting math that goes on behind that, and a lot of interesting economics too that goes into money and banking. So a little aside there, but I thought they were good questions from the text. And, there are economic reasons for all of these things. And mostly it has to do with just supply and demand and incentive structures, creating an incentive for people to do business with them. Okay, so next example. So here we're going to get into an example or two that I think are maybe a little bit more interesting and nuanced than some of the previous ones. We're going to use the formulas that we had used before, but oh yeah, sure. But we're going to try to answer a broader question. And what we're going to see is that when we're trying to answer a broad question, the math, the modeling, and so on, the applications of some of this stuff that we're talking about can be a part of the discussion, but it's not going to necessarily be the entire discussion. It's not necessarily going to be the numbers came down this way, so this is what we do. Occasionally it does come down to that, but often it doesn't. So suppose that Tom has an investment portfolio containing mutual funds. And mutual funds is basically just a way to invest money in stocks easily, more or less. And it's worth $10,000. So this is like Tom's retirement account or something. Tom has a car loan for $12,000. The investment portfolio has returned 8% interest per year for the past 5 years, and Tom looks at the economic situation and expects similar results in the future. And the car loan has an interest rate of 14% per year. Now, Tom can basically do two things. I mean, there's, of course, a lot of things that Tom could do, but from this perspective, Tom can keep things as is, keep the $10,000 invested, and continue to pay monthly on the car loan. Or Tom can sell off the investments and pay off the car. Or, well, almost pay off the car. Pay off most of the car. to pay off most of. And the question is kind of what should he do? Well, you know, and there are a lot of factors that come into play here, but one thing we might want to look at is the two scenarios. What is basically the cash flow? So if Tom owes $12,000 at a rate of 14% per year, well, his interest per year is going to be the principal, 12,000 times the rate, 14% times time, let's say 1 year, or that's 12,000 times 14 over 100 times 1 year. 12,000 is 120 times 100, so that's 120 times 14. And let's actually, so instead of 1 year, let's do per month. So this would be 12 times 140. This would be dollars per year that he's paying in interest, but he's paying $140 per month in interest. So he pays $140 per month in interest under scenario A, keeping things as is for the car loan, but he earns from the investments $10,000. It's going to be the same formula, I equals PRT, times 8%, times 1 year. Or that's going to be $10,000 is 100 times 100, or that's going to be 100 times 8, or $800 per year that he earns from the investments, or 800 over 12 per month that he earns from the investments. 800 divided by 12, well, there's a factor of 4 in both of those. That's 200 divided by 3, or that's about $67 per month earned from the investments. So scenario A, from the car loan, it's costing him $140 per month, and from his investments, he is gaining about $67 per month. Scenario B, what would that look like? If he paid off most of the car loan, if he took this $10,000, pulled it out of the investments, paid off the car loan, he'd only have a principal of $2,000 left on the car loan. So he owes $2,000 now, doesn't have any money in investments, so that's not generating interest for him from income, but he doesn't have to pay as much interest for the car loan. So now it's $2,000 times 14% times 1 year. So we'll start out figuring out how much interest per year and then divide by 12 to get interest per month. Well, 2,000 times 14 over 100, that's 20 times 14. Or 20 times 14 is what? Yeah, 280. That's dollars per year. And then to figure out his monthly interest that he has to pay is 280 over 12. There's a factor of 4 in both of those. That's 70 times 4 is 280, and 3 times 4 is 12. Well, 70 is 60 plus 10. 60 over 3 is 20. and then 10 over 3. So that's about $23 per month. So in scenario B, he owes $23 per month. In scenario A, what's his net? That's negative 140 plus 67. Well, my answer is negative, and it's negative of 140 minus 67. I need to borrow from the 4. This gives me a 3. 13 minus 6 is 7. So in scenario A, where he keeps the investments, the $10,000 in investments, returning him 8%, but he's paying that 14 on the car, we can just see that there's a disparity there, right? He's earning 8 from investments, but losing 14 on the car. He's paying overall, basically, he's taking money from the investments, at least philosophically or in theory, even if he's not practically doing this, taking that 67 from the investments, paying that towards the interest on the car, and still has to come up with 73 more dollars to pay towards the car each month. On the other hand, if he pays down the principal of the car down to $2,000, he's only paying $23 a month now in interest. Paying the money towards the car is the much better financial option as far as the numbers go. Now, there are pluses and minuses to this, right? If he pays a bunch of money towards the principal of the car, well, that's going to free up monthly cash flow. So his expenses per month are going to be less. Now, that means that if he wants to build his investments back up, he can do it more quickly now because he doesn't have this car loan that's cutting into his cash flow each month, or doesn't have nearly as much of a car loan. He can build those investments back up very quickly, but that requires that he's disciplined with his money. That requires that he actually takes, this, what is it, $50 or so less expenses that he has per month, and actually allocates that $50 per month to his investments. And then when the car loan is completely paid off, when he gets rid of this 2,000, he allocates the entire car payment, that he was paying to investments. So if he's, disciplined about that, if he has, managed money well in the past, paying off the car is probably a good, or paying down the car loan is probably a good investment, because he's getting rid of a 14% detriment instead of holding on to an 8% benefit. Now, on the other hand, if he's not disciplined about his money, and if he says, oh, if I have the extra $50, I'll spend it on, a night out with friends or something, more likely than save it. Well, then the car loan is almost like a forced savings account, right? If he says, this is my investment money, I'm not going to touch it, I'm going to leave it in there. Well, if he doesn't pay the car loan, the bank calls and says, hey, where's my money? If you don't give me my money, I'm going to take your car. If you don't put your money this month into your investments like you were planning, you're probably not going to get anybody calling you, pounding on the door and saying, where's my money? Right? So somebody who's a little bit less disciplined with their money might choose the by the numbers less optimal way of going about it, keeping the car loan and keeping the investments separate, because they've kind of already allocated that mentally as, these are my investments, I'm not going to touch those. And then the car loan is, their cash flow is going to the car loan. That's costing them money every month, but maybe it's worth that price. That's an economic price for an economic benefit of cordoning off their investments and, having that protected money, so to speak. So this was actually a fairly real life scenario. One of my buddies was in a pretty similar scenario. He said, look, I want to build up my retirement account. How should I do it? He's very good at managing money, but just doesn't, always know all of the academic sides of finance. And that's basically what I told him. I'm like, dude, pay off your car. You're saving this huge amount of interest, you're saving more money than you'll ever make in the market by paying off your car, own it free and clear, and then use that extra cash flow and just, just have it taken out of your paycheck. Just tell HR, like, whatever your car payment was, take that amount of money and just divert it to your retirement account. And so he did that. And I think that's worked out pretty well for him. So definitely not financial advice. I'm not saying you should do this or you shouldn't do this, but you can see how there are a lot of factors that come into play in a decision like this, but this is an important part of it, being able to run the numbers and see what the different scenarios are. Seeing that if I choose option A, maybe I do choose option A, but it's going to cost me $50 a month relative to option B. Or if I choose option B, that's going to save me $50 a month, but that comes with its own trade-offs. So at the very least, by being able to run the numbers, we can understand what the trade-offs are and make hopefully more informed decision. Okay. And a similar example here. So suppose Lisa has a home mortgage with a principal of $120,000 remaining to be paid off over 20 more years at 3% per year. Lisa receives some inheritance money of $150,000. She can invest the full inheritance at a rate of 7% per year, or she can pay off her mortgage and invest the remaining $30,000. What should she do? And I'll leave the numbers to you. It's quite similar to the above problem. Exercise, do the numbers for both. But just speaking a little more generally, we see that the home mortgage is actually costing us not very much, 3% interest per year, and we stand to make 7% interest per year in the market. Is again fairly realistic numbers. I mean, maybe not over the past couple years. If you have a new mortgage, it might be at a higher rate than this, but this is kind of a bad time to originate a mortgage and wait a couple years, and then it'll come back down and you can refinance or whatever. But according to the numbers, it's kind of the opposite of the scenario up here. Paying off the car made sense because we were paying 14% and earning 8%. Paying off the car essentially meant that we were making 14% on the quote investment of paying off the car loan or paying down the car loan. I keep saying paying off, I mean paying it down. We were essentially making 14 by avoiding that interest we have to pay to somebody else. Relative to making 8, that was the better deal. Here, if I pay off the house, I'm essentially making 3% per year, but I could be making 7%. By the numbers, it makes more sense to keep the mortgage and keep the investments. And particularly if you're young and you have a stable job and you have a decent amount in savings, which certainly now she does have a decent amount in savings, that's probably what most financial advisors would say. Hey, your mortgage rate is low. Also, by paying your mortgage each month, you're maintaining credit. The bank handles a lot of things like property taxes for you, which is also kind of nice. Just not to have to deal with that. They handle all that through escrow. So all of that is pretty nice. And what's the benefit of paying off your house? It feels nice to have your house paid off, but that's maybe the main benefit. As kind of a side note, you never really pay off your house because, people think that like, oh, I paid off my mortgage, I don't have to pay anybody anything now, but you still have property taxes. So you're still like, and property taxes, depending on your location, can be like, 30%, 40% of your monthly payment. When you pay your quote mortgage payment, some of that goes to the principal of the mortgage, some of that goes to interest, some of that goes to homeowners insurance, which is typically paid through your bank. They want to make sure that your house stays insured so that their asset is insured. And then some of that goes to pay property taxes. Your bank tells you, it figures out how much property taxes you owe and tells you how much to pay per month for that also. So, if you have a mortgage that's say $1,000 a month, and you pay off your mortgage, you might still be paying $500 a month between your property taxes and your insurance and all of that. Um, so it's not as nice as it sometimes is marketed, paying off your house. But if you're young, if have a steady income, maybe keeping the mortgage and putting the money in the market, letting it grow at 7%, it's only costing you 3% to access that money. You make a nice margin there. If you're a retiree, well, now you're on a fixed income, things are a little bit more shaky. Um, people would, in that situation, would often prefer to pay off the mortgage just so that there's one less variable floating around. There's one less piece of risk, right? Um, you know, that's not exactly my perspective, but who knows? Maybe in 30 years when I'm retired, maybe I'll have a different perspective and I'll want my house paid off. But in my mind, hey, if you can access money at 3% and get a margin of, and invest at 7 to 10%, if you can get a margin of 4, 5, 6 percentage points, and even after you pay the tax on the investment income, um, I'd I'd probably keep the mortgage. But I guess maybe it's kind of cool to say that you don't owe anybody anything. So anyway, so that's another example where the rates are flip-flopped a little bit. Any questions on any of these applications on interest? So these last two hopefully give you a little bit more of a kind of a realistic scenario, where the dollars and cents, the calculations are part of the discussion, but not the full discussion. And as an aside, this is, why financial advisors are, um, or can be very beneficial, is they can talk you through all of these different aspects and you can understand what trade-offs you're making if you take this approach or that approach. What are you giving up versus what are you getting, and what are you most comfortable with there? Okay, so moving on then to section 6.5, solving proportions and their applications. So let's start off by just looking at what a proportion is. And here we have two things that are related to one another. 7 is to 9 as 35 is to 45. You might have seen these in the past written something like 7 is to 9 as 35 is to 45. I mean, I don't know who fell in love with the colon or something, but they would sometimes write them this way. I think that was the right notation. We're going to write them more as fractions. So we're not going to write them in such a convoluted notation. So we have a ratio, 7 is to 9, 7 relates to 9. We're saying in the same way that 35 relates to 45, that it's proportional. So this claim is that 7/9 equals 35 45ths. And we see that this is true. We can verify that this is true by looking at 35 over 45. I note that both of those have a factor of 5, 7 times 5 over 9 times 5. My 5's divide out 7/9, and I verify that this is a correct mathematical statement. Another way that I could verify this is I could do what's called cross multiply. I could multiply both sides by 9, giving me 7 times 9 divided by 9 equals 35 times 9 divided by 45. And then I can multiply both sides by 45. That bumps the 45 to the other side. So cross multiplying, if it's true that 7/9 equals 35 45ths, then I can multiply 7 times 45, multiply 9 times 35, and those should be equal as well. That's a more challenging calculation to carry out, but those are equal. So let's look at each of these and determine whether each is a proportion. So let's look at 5/12 equals 45 over 108. Is that a true mathematical statement? It might or might not be. Normally, we wouldn't write something equals something unless we knew that it was, but here we're saying somebody told us this, and we want to evaluate and see whether it's true. So how could I evaluate whether this is true? I could, I suppose, cross multiply. So this is true if and only if 5 times 108 equals 45 times 12. Well, I see I could divide both sides by 5. That might make things a little simpler. So this is true if and only if 108 equals 45 divided by 5 is 9 times 12. And what's 9 times 12? 9 times 2 is 18. That is indeed 108. So that's true. 108 is 9 times 12. So this is true and this is true. Yes, this is a correct proportion. It's a correct mathematical statement. Is it true that 11/6 equals 21/16? Well, again, we could cross multiply. That's true if and only if 11 times 16 equals 21 times 6. I guess I can make things a little simpler by dividing a factor of 2 out of both sides. I see this as true if and only if 11 times 8 times 2 equals 21 times 3 times 2. And I could divide both sides by 2. 11 times 8 is 88. Is that equal to 21 times 3, which is 63? No. So this 11/6 equals 21/16 is not a proportion. It's not a correct mathematical statement. So we could look at solving equations. Let me put these on a different line so that they're a little bit easier for you to read. Can actually zoom in a little bit too. We don't need as much room here as we did up above. So we could look at something like this, for instance, solve x divided by 56 equals 7/8. And I could solve this a couple different ways, but I could just go ahead and cross multiply. I can do 8x equals 7 times 56. Now that just cleared my fractions. I don't have to deal with fractions anymore for my equation solving steps. I see I have number times x equals number. I'll divide both sides by 8. I note that 56 has a factor of 8 in it. 56 is 7 times 8. My equivalent fractions property, I can divide out the 8s, and 7 times 7 is 49. So we see the proportion would be 49/56 equals 7/8. That would be a valid proportion. That would be the value of x, the numerator associated with the 56 that we have to use to make this a valid proportion, a valid mathematical statement. Something like this looks a lot more complicated because the variable is in the denominator, but actually the steps are basically the same, right? I just cross multiply. 72q equals -6 times 156. I see I have number times variable equals number. I divide by the coefficient of the variable. Q equals -6 times 156 over 72. I know that 72, I think, is 6 times 12, right? So this is -1 times 6 times 156 over 6 times 12. My sixes divide out those factors. And 156 over 12, let's see if that divides out nicely. 12 goes into 15 one time. 12 goes into 36 three times. No remainder, nothing else to bring down. 156 over 12 is 13 times -1. So Q has to be -13. In other words, 72 over 156, to make this a proper proportion with -6 in the numerator, I need a -13 in the denominator. That would be a correct proportion. That would be a correct mathematical statement. So we got to zoom back out a little bit. There we go. So let's look at a few examples here, a few applications. So Kevin wants to keep his heart rate at 160 beats per minute or above while training. During his workout, he counts 27 beats in 10 seconds, right? This is like if the nurse like feels your pulse, a lot of times she's not going to feel your pulse for a whole minute and count all of that. She might count 5 seconds or 10 seconds, something like that. Counts 27 beats in 10 seconds. How many beats per minute is this? And is Kevin currently meeting his target heart rate? So here I have units in play. And nurses a lot of times have to do similar calculations to this, right? I mean, one is this exact calculation, estimating somebody's heart rate and beats per minute based on a shorter time interval. But they might have to do medication, dosing, things like that. So we're going to use dimensional analysis here. We're going to look at these units, beats and seconds. And what I'm going to say is I want to know how many beats per minute. So the answer that I want is in beats per something. So I want to construct a proportion where I have, say, beats per second on both sides, let's say. Well, beats per second, the data that I'm given is 27 beats per 10 seconds. And what I want is beats per minute, or well, a minute is 60 seconds. So I want the number of beats per 60 seconds. This helps me keep everything lined up the right way, right? If I was not being careful with my units, I might end up getting a 60 up top here or something like that, or I might get like a 1 in the denominator or something, but I know that the seconds have to line up. So 27 beats in 10 seconds is equivalent to, say, X beats per 60 seconds per minute. Or I have X over 60 equals 27 over 10. Or I have 10X equals 27 times 60. And divide through by 10. X equals 27 times 60 over 10. The 60 divides out with the 10, giving me a factor of 6 left over. And I think this is pretty sensible, right? We know that 1 minute is 6 lots of 10 seconds, so we should have 6 lots of 27 beats occur in that time frame. Maybe plus or minus a couple beats, right? But what's 27 times 6? 6 twos are 12, plus 4 is 160. So that's 162 beats per minute. Has he met his target heart rate? Yes, his current heart rate is above 160. And as a side note, we could kind of an aside to this problem. If we knew that our target heart rate was 160 beats per minute, I could say 160 beats over 60 seconds is how many beats per, we could say 5 seconds, something like that. I can figure out what X is, and then I know that, at whatever point uh in my exercise routine, I'll, you know, do my pulse for 5 seconds, count the number of beats, and see if I'm in this ballpark of what I would get for this number. So I could go the other direction as well. Or if I didn't think 5 seconds was accurate enough, that I might, make an error with starting or stopping the time or counting the number of beats. Maybe I would go to 10 seconds or 15 seconds. But if your heart rate's up at 160, it's going to come down pretty quickly if you stop exercising and start counting your number of beats per minute. So, okay. So next example, April wants to paint the exterior of her house. 1 gallon of paint covers about 350 square feet, and the exterior of the house measures approximately 2,000 square feet. How many gallons of paint should she buy? So we have 1 gallon covers 350 square feet. So X gallons cover 2,000 square feet. Right. Or we have 1 over 350 equals X over 2,000. Or this tells us that 350X equals 2,000. Or X equals 2,000 over 350. I can divide a factor of 10 out of both, so that's 200 over 35. And, well, 200 over 35, I mean, doing long division doesn't help me a lot. So 35 times 5, what does that give me? 150 plus 25 is 175. 35 times 6 is going to be 175 plus 35, or that's 175 plus 25 plus 10. That's 200 plus 10. That's 210. So 200 over 35 is between 5 and 6. So to paint the outside of her house, she would need between 5 and 6 gallons of paint. So she could kind of go either direction here, right? I mean, the mathy answer is buy 6, because if you bought 5, you won't have enough. The practical answer is it's probably going to take you a few days to paint the house, and buy 5, as long as you can, go back to like the store and get the exact same kind of paint and all of that, as long as you're confident that they'll mix it right the next time, which if you're not confident, then buy 6 all at once and get them all the same color. But if you're confident they'll mix it right, if you're going to a decent store, that shouldn't be a problem. I mean, if it were me, I'd probably buy 5. And if I start to run out, if I say, okay, I don't think I'm going to make it, then I'll go back and buy one more. But heck, if you've bought paint for anything recently, paint has gone up dramatically in price. So I don't think I would, want to buy a 6th one and end up, just not using it or something. So again, all of these, like when you transition to a real life question, how many gallons of paint should you buy? It's a little more complex than this, but this at least gives you the answer. Mathematically speaking, if a gallon covers exactly 350 square feet, and if your house measures exactly 2,000 square feet, the paintable area, then you'd need 6 gallons because you'd need a little more than 5. But practically speaking, right, I mean, the coverage is going to be dependent on how thick you paint and all of that. The area of your house, the square footage that you have to paint was probably approximated. I mean, if 2,000 square feet is actually, 1,850 square feet, and if it covers a little more because you're painting a little less thickly than, than the way they recommend or something, then maybe you get away with 5. Okay, we also can solve percentage problems by thinking about them as a proportion. So what number is 75% of 920? So what number X is 75 over 100, 75% times 920? We can see that we could think of this as a proportion. The proportion of X to 920 equals 75 over 100. So 75 parts out of each 100. If I have 920 total, how many parts out of that do I have? I can rephrase percent questions as proportions. So percents and proportions, very similar ideas, very closely related ideas. Or 25 is 80% or 80/100ths of what number? Well, I see that 25 over X equals 80 over 100. So this was my percent on the right-hand side. Same with down here. Or what percent of 92 is 46? So 92p equals 46. Or I see p equals 46 over 92. Or p I can think of as a number over 100, say x over 100 equals 46 over 92. So since there's like this one-to-one correspondence between percent questions and proportions, and we know that proportions look like A over B equals C over D, well, if it's a percent question, at least one of our denominators has to be 100. My 3 types of percent questions really just correspond to which one of these 3 variables, A, B, or C, is missing. Is it the numerator of the percent side? Is it the numerator of the other side, or the denominator of the other side? That's what gives rise to my 3 different types of percent problems. We're not going to solve these, but just showing that there's this nice one-to-one correspondence between percent problems and proportions. They're essentially expressing the same thing. Okay, next example. We actually might, this is our last example, actually. We're going through this more quickly than I thought. Okay, so next example and last example for today, we might wrap up just a little bit early. Travis is going to wash his car. The directions on the bottle of car wash concentrate say to mix 2 ounces of concentrate with 15 ounces of water. If Travis puts 6 ounces of concentrate in a bucket, how much water must he mix with the concentrate? Our units are all in ounces, so that's kind of nice. So I'm going to set this up as amount of concentrate per amount of water. I could set it up the other way too. I'll do it this way. We could set it up as water per amount of concentrate. So on one hand, we can mix 2 ounces of concentrate with 15 ounces of water. That will be the correct proportion of concentrate to water. On the other hand, if we want to use 6 ounces of concentrate, how much water do we need in ounces? We'll call that X. we have a proportion problem. Here, x is in the denominator, but again, if it doesn't really matter because the first thing we're going to do is cross multiply. If you had set it up as units of water over units of concentrate, you'd have got x over 6 equals 15 over 2, and you would get the same answer. So I see that 2x equals 15 times 6. Again, I have number times x equals number. This tells me x equals 15 times 6 over 2, or the 6 divided by 2 just makes a 3. So he needs to mix 45 ounces of water with the 6 ounces of concentrate so that it's in the correct proportion of water to concentrate. Where you don't want to just make it all like slimy, you want the car wash to be able to bubble up and make suds and so on. You also don't want it too diluted. If there's too much water, then it doesn't actually clean anything. So he needs 45 ounces of water to go along with this 6 ounces of concentrate. All right, any questions on anything we did today? Right. I thought this would take us a little bit longer, so I wasn't planning on starting chapter 7 today, and I think we could have gotten an okay start on it, but I didn't expect to have a full half an hour left. So when we come back next time, we're still, decently on schedule. We have a couple of kind of break days coming up, so that'll get us fully back on schedule. But when we come back on Thursday, we will start into chapter 7, which is the real number system, and starting to talk about some more general properties about the real numbers. A lot of this we'll have seen before in some different contexts, but we'll be taking another look at it and continuing on with chapter 7 starting on Thursday. Let me stop the recording.